This is a lecture for AQA Discrete Mathematics, Game Theory, Section 2.1, 3x3 zero-sum games. Well, here we have a payoff matrix for a zero-sum game for two players, player A and player B. As always, the information on here shows what happens for player A. So this is the gain for player A. If it's a negative value, obviously player A is losing. Zero sum just means that whatever happens to A, the opposite will happen for B. So if player A loses 4 here, then player B is gaining 4. Now you've seen already how to handle games where we've got 2x2, 2x3 or 3x2. That's referring to the number of different strategies that are available to each of the players. And what we want to do in this series of videos is to develop methods for handling 3x3 games such as this one. Before you go on, therefore, it would be quite a good idea to review the work that you've seen previously and make sure that you do know how to handle these smaller games. Well, to start off with, a 3x3 situation is no different to what we've seen previously, so we should first of all check for the idea of a stable solution. So to do that, we need to look at the row minima. In other words, the minimum value that occurs in any row. These are -2, 1 and 2, and the column maxima. So these are 5, 2 and 4. So remember that the play safe strategy for A is going to be where we have the row maxi min value. So the largest value of the row minima, which here is at 2, so this is the maxi min value, and we want the column mini max value, so the smallest value of these maxima here. This is the mini max value, and we can see that therefore that A should play R and B should play Y. The other thing we can tell from this is that the maxi min value is equal to the mini max. So here we've got maxi min is equal to the mini max value. So this solution is stable. So to do that, we looked at the row minimum values and the column maxima and found the row maxi min and the column mini max values. And we could say therefore that the play safe strategy for A was R and for B is Y. And because these are equal to each other, the values rather equal to each other, both equal to 2, then this is a stable solution. We say we have a saddle point or a stable solution at Ry, and the value of the game is 2. This is from A's viewpoint. Now, because this is stable, there's no value in either of the players changing from the strategies R and Y. There would be no advantage to them at all in doing that. Well, here are two different games where the situation is not stable. So if we look at the first one, the one on the left here, we can see there we have the maxi min value and here the mini max value. So these are not equal to each other. So there's going to be some incentive for A or B to change from their play safe strategies. Likewise, in the one on the right, got the maxi min value -2 and the minimax value of 2. So again, some value in them changing from their play safe strategies. Let's just consider that idea in a little bit more detail. So for example, if A is playing P, which is the play safe strategy, and B is playing X, then A knows that they're going to lose 2 units. So A thinks, well, okay, if I change my strategy, let's say to Q, I'm only going to lose 0. In other words, we'll end up even. On the other hand, B is thinking, well, A may change, so what if I was to change then to Z, and B would end up with 4 units rather than the 2 that they had. So there's advantage in making changes, where in the previous example there was no advantage, so they would always play their play safe strategy. So now we have this idea of trying to find a mixed strategy. The final step before we go on to look at the mixed strategy is to see if there's any dominance involved in these games. By dominance we mean, is there one row or column which is always going to be better for player A or player B? So if you look at the one on the left here, you can see that R is always worse for player A than P. So you can see that if they played P, they're losing 2, or 3 if they played R while B is playing X. And it's true that for all these different values, so -2 is better than -3, 1 is better than 0, and 2 is better than 1. So therefore we can say that P dominates R and we can ignore R. So we reduce it to a 2-by-3 game. If you look at the same situations for the second of these, however, you'll see that there's no dominance involved here. So this remains a 3-by-3 game. In a situation where there is dominance and we've managed to reduce it to a smaller game, so 2-by-3 in this particular case, then the methods that you've met previously, the graphical methods, would become available. And so, as I said before, you should really make sure that you know those graphical methods and could apply them to this particular situation. However, in a situation where we've got 3-by-3, obviously we can't use a graphical approach, so we need to come up with some different way. And to do that, we can use the idea of linear programming. So we're going to look in the next few videos at how we change this 3-by-3 situation from its tabular form into a linear program. And of course then we have methods that we can solve linear programs for 3-by-3 situations. So the next video we'll look at formulating the game as linear programming, and then after that we'll look at how we then solve it.